Hello, everyone. This is Dr. Rocío Pérez de Prado, Associate Professor at the Telecommunication Engineering Department in the University of Jaén in Spain. It is such a pleasure to greet you all and to contribute to ICETOL 2024, this fourth international conference on educational technology and online learning. So I'm going to make this presentation of a work titled Computer-Assisted Platform for the Intuitive Learning of Electromagnetic Modes Propagation in Broadband Domestic Optical Fiber Networks. I must say that this work has been developed considering the collaboration of diverse professors in my department, Telecommunication Engineering Department, and also the help of a telecommunication engineering student, which has been useful not only because of his technical help, but also because of his impression of a student of this learning process. Okay, so basically this is the index. The thing is that, basically I'm going to file this the structure suggested by ICETOL for the papers. And therefore, when we're going to talk about this in an introduction and methodology results and conclusions. Okay, so what is this work about? Okay, so today we live in a world in which, telecommunication is essential. And within this telecommunication field, there is a king or a queen of transmission medium, wired transmission medium, which is this optical fiber. Okay, the king or queen of wired transmission systems means that this optical fiber is able to offer the highest transmission rates in the longest distances. And indeed, this is a key aspect. It is something that is supporting the development on important technologies today, like we could talk about cloud computing, IoT, 5G, 6G, wireless technologies, grid computing, so many others. And so for telecommunication engineering student, it is such important to understand the concept behind this technology. Okay, it is essential because it is a tool that allows them to know its limitation and how to overcome or how to avoid them to take advantage. So this me as a professor of optical communication for more than 12 years now, I think that it was essential to make these students more able to intuitively learn about these concepts, which are not easy, but they're essential. Okay, so somehow I think I could contribute with some ideas. So basically, this idea is to develop a step index optical fiber analyzer, mostly focused on domestic sections. And this tool should start from the introduction of physical parameters of the fiber and also the working frequency. And from these parameters, the student would be able to see what is going on within this fiber. Okay, so particularly there were some specific objectives. I want them to learn with this tool which are the propagating modes, the access modes, which are the propagation constants, the nomenclature, the name of these access modes, and also the name when they are aggregated in terms of linear polarized modes, when they are degenerated in with guided condition. And also was essential of this tool was able to, it is capable of be deployed in Windows and Mac systems, okay, because this is the most typical used applications, system operating systems that my students have, okay. So basically, the methodology for this tool is based on the electromagnetic theory that it is brought by optical fiber in a step index optical fiber. So we must start from Maxwell equations for linear, non-dispersive in time and space, homogeneous, isotropic, not magnetic and free charge medium. And from this, we could be able to deduce after a more or less long derivation, which is the dispersion equation. Okay, the dispersion equation is a key factor because it's giving us the chance to know how many modes are going to be transmitted, the value of the dependence of the wave with the longitudinal axis, that means beta factor, and it's going to give us not only the number and the propagation constant, but also the type of modes, But this is also a key because of the inherent characteristics of the different type of modes. Okay, so basically we could say that the need of this tool is to solve this dispersion equation. And a key aspect that is that we are going to be able to solve this analytically. It is not possible. So the typical way to solve it is doing it using numerical methods. Okay, there are many ways to do so, but okay, a good point for us in telecommunications is to do it using programming. Okay, so this is basically the core of this. We're going to program, and we're going to program in order to be able to solve this spatial equation in a way that we are able to analyze the main conclusion that we can derive from this equation. Okay, so if we obtain the possible values of beta, we're going to be able to know the number of propagation modes, the type of propagation modes, and the value of this constant, so the dependence with the optical axis, okay, the associated parameter. So we have to solve this spatial equation. How can we do so? Okay, we can do it considering, first of all, some simplifications. Okay, if we take into mind that there are different modes, we have it here. We can have TE0M modes and TM0M modes, which means this type of TE, T, or TM modes corresponds to always to modes with first index 0. This means, okay, that in this case, in the first case, we have the electric field components in the longitudinal axis will be 0, and that the field component in the magnetic longitudinal axis would be 0. Okay, and also on the other hand, when we have the B is greater than 0, we're working with EH modes or E modes. Okay, so we can divide the problems, considering there are going to exist different types of modes, and it's going to give us a simplification that we're going just to see in a few seconds. And also, we will also have to bear into mind that propagation constants in an optical fiber, considering weak guide conditions, is always to be bounded by these two values we have here, which are the refractive index in the core multiplied by the wave number of Mice channel, and the propagation constants in the cladding multiplied by the wave constants. Okay, so considering these two aspects, we can get to simplification. We can derive from this dispersion equation, we can obtain this transcend equation for the different types of mode. Okay, so now the problem is divided into 3 different problems. Also, we know that because we're going to consider with guided grid conditions, this is even has a mirror more simplified form. Okay, so bear this into mind. And now basically what we have to do is to apply numerical methods. Okay, so if we take a look at this transcendent equation of algebraic equations, we're going to see that we have 2 terms. So we're not able to obtain from here the values of beta directly, it would mean analytically, we're going to be able to solve it using numerical methods. Okay, so what we're going to do is to represent each part of the equation graphically. Here we will have this part of spatial which correspond to these vertical curves, and then we have the other terms of the equation for this horizontal curve. Okay, this would be a case for those modes corresponding to the first index with V0, okay, TE or TM modes. So when we find intersection, it's where we're finding a possible value for beta. So basically what you're going to do is to iterate for different values of beta, and the values of beta we're going to consider are those in this guided mode condition. And that's when we have it, when we're going to iterate this instruction to observe this intersection. Okay, but this is not only going to be useful or necessary to obtain graphically, to graphically obtain this intersection, but also you're going to be interested in obtaining an automatization of this. Okay, so we've obtained these graphical curves, and then we have to automate the obtention of these specific values, and we also want to know the nomenclature. Okay, exactly which specific code will we obtain. So once we have been able to obtain the exact modes of my optical fiber, then a second step will be to analyze the linear polarized modes. We are going to always to be present, and we can consider them in waveguide condition. That is when we have the core, the refractive index in the core and the refractive index in the claring are much close. Okay, so we know the connection between the exact modes, and we know the connection with the linear polarized LP modes. So again, we also want that our application is also able to offer us this information. Okay, we know the characterization of the fiber. Please tell us in the degeneration mode. Okay, so this basically we have the results. So first of all, in our application, which is made up using MATLAB app designer in the version of 2019A, we are going to be able to introduce the basic aspects of basic parameter of optical fiber, which corresponds to technological parameters. This means we're going to introduce the radius of the fiber, we're going to introduce the refractive index in the core, the diffractive index in the claring, and also the working frequency in the terms of wavelength that it is usual in optical fiber. Okay, so here it can be observable that in this representation that we are going to be able to obtain graphical solutions for the different modes. Okay, doing these iterations using numerical methods, as we'll see before, where the interactions correspond at the specific value, and the number of intersections will represent the number of solutions. So before we've seen the graphical representation for the more simple modes where TE and TM, but we also must be reminded that there are more complex solutions for the HE, where we have different values of B. So for every value of B, okay, not like 0, B0 was the only possibility for TE, TM, but for HE, EH, we have different values of V, so we have to iterate for the different value of B and graphically obtain the solution. And once we've obtained the solution, we can see in this modes table that we've been able to what? To obtain the nomenclature. Okay, we will have the different index. We have the B would be the first index, and we have M would be the second index. So we know the nomenclature of the different propagating modes, and we know the propagation constant. Okay, so this would happen for all the modes, and this is a more complex example because we are considering EH or HE modes. And finally, we'll also have the possibility to analyze the LP modes that we've seen before. So we know the exact modes, and we know that degeneration happened when we consider waveguide condition. So the tool is going to graphically be able to give us this information. Okay, we know the exact modes, we know the linear modes, we know the associated propagating constants for the connected modes, and also the frequency from which these modes would start propagating is provided. Okay, so we can simulate with different parameters. You know, you have these slides. Is something useful, quite intuitive to use. Of course, the regions are delimited to those values which are coherent for the typical infrastructure in private to the home in the client sections, in a way that also students get used to these typical values. Okay, but the use it's quite straight. Okay, so basically, I would like to conclude saying that with this work, we basically have intended to offer our students in telecommunication, engineering, and particle in optical related subjects in which signal propagation must be analyzed with a visual interactive computer assisted platform to help them to achieve a better understanding and knowledge of the electromagnetic propagation of the fiber. And also we want our students to design complex fiber to the home infrastructure systems because of their own experimentation. Okay, so propagation is essential in some parts of the design. Okay, they're going to get this knowledge from their own experimentation by touching, by playing. So we think this is key, even more considering the difficulties of these concepts. And also, it is a key aspect that they're going to be introduced for numerical methods. Okay, sometimes we have these complex equations which are not solved in a straight way, and we are all going to be able to do so using numerical methods. Okay, it is very hard to do it by scratch. So you have this tool which is going somehow graphically is going to teach you what numerical method is going to mean. And also, it is a key factor that we have bear in mind that we must offer somehow an application that could be deployed in both Windows and Mac operating systems, because this is what more of our students use, and it should be something that it couldn't it was not going to bring them problems in order to use. And so we bear into our mind also this in our work. So I think that is all. Thank you very much for your attention. I hope that this tool motivates some of my colleagues in telecommunication engineering for the studies of optical systems, and that you find some ideas useful. So thank you very much, and see you soon.